Okay, thank you very much, Raphael, for a nice introduction. I'm glad to be here, MoMaS, once again, after a couple of years. And what I would like to present to you is a joint work with many people. So there are some of them in the audience. Clement is sitting right there. Daniel was here, I think, on Monday, Tuesday. Alexandre just left. Eric Florent, he is at the French Petroleum Institute. Iliu is a colleague who works in Eindhoven. Well, Mary Wheeler in Austin, Texas. And Soleiman did a lot of the computation in the very last part of the talk. And he was a PhD student and is now in the French Petroleum Institute at the research position. So that's the content of the talk. And as you see, there are basically three parts. Here I would like to describe the methodology, which starts with this name. It's inexact Newton method, an algorithm that you probably know, and an adaptive version of it. So some motivations, how does it work? And then I would like to spend a lot of my time on two-phase and then multi-phase, multi-component. I think the two problems really related to MoMaS mathematics, and show you how this methodology applies in these two problems. So what is the motivation and introduction? So that's for starting from the end. So if you have in this multi-phase, multi-component setting, what is it typically? And we've seen many examples. So it's first some partial differential equations, typically coming in a system, being nonlinear, possibly degenerate. They do not come just alone. They typically come with some algebraic constraints. So this is already quite complicated, and what you of course want to do, some numerics. So you take your favorite discretization scheme, and the main point of my presentation today is when you arrive on a given time level to a large system of nonlinear algebraic equations, and the ways how you can efficiently solve these large system of nonlinear algebraic equations. So the goals is to show you how the theory of a posteriori error estimation can be used for such complicated problems. First, to give you an upper bound on the error, so you know how big is the overall error, and not only one number, one quantity, but you want to distinguish the different parts of the error, or coming from the different parts of this procedure. So in particular, have a error in time, coming from time stepping, error in space, so that you can do mesh adaptivity, and well, it was in bold here, error in linear solver, which is at the very end, and error in some iterative linearization. And when you have this error, you can derive stopping criteria, so both of these solvers, the linear and the nonlinear solver. So that's the picture. Okay, so first part of the talk, model, problem, steady situation of a quasi-linear elliptic case. So you look for a vector function sigma, which can depend on, in a nonlinear way, on the unknown u or on its gradient. And you know that the divergence of this sigma with a minus sign should be in equilibrium with known load f. This is for simplicity, very simple boundary condition. Of course, in practice, then we run with inhomogeneous and other types of boundary conditions. So just a little bit for mathematics. For this model problem, we need to pick a right setting. So we have some Lebesgue exponent p, it's dual q. We need this right-hand side to be in the correct space, which is the LQ. And to fix ideas, a typical example for the considerations in this part is the P Laplacian. So this nonlinear vector function is only dependent in a nonlinear way on the gradient, and it takes its Euclidean norm to the power p minus 2. So that's my model problem for the first part. And I don't want to specify too much about the way how you attack numerically a problem. all I wanted to stress that at some point you have this large system of nonlinear algebraic equations. You start to do some linearization. It gives you, on a given step k of linearization, some intermediate result. And this is a system of linear algebraic equations that you need to solve with your favorite linear solver. So you've got another iteration index I, and that's the one for algebraic solver. So basically, in the procedure on step k and step I, you will have something. And this something is this UHKI, and that's input for us. I'm not detailing whether you got it from finite volumes or finite elements or something else. So this is a kind of meaning of this VTH. It's to say that the approximation can be also non-conforming, discontinuous, or coming from finite volumes or DG. So it's not necessarily a nice conforming function. And this will be the quantity that I will be working with all the time now. So your approximation during the solution of nonlinear algebraic system. And of course, what I want to do to estimate the error inside. And in order to arrive at this, I will develop a theory which will just hang on 3 assumptions. And then the application to your favorite scheme will be the verification of these assumptions. So I've put all of them together. And you see the first one. And the first one requires us on each nonlinear solver step k and linear solver step I to find some vector, this THKI, sitting in the proper space, which, well, is here HQ diff of omega. And if I go one slide back, I knew that my sigma, the weak solution, should be such that the divergence with minus is f. So what I require from my vector field that I would like to have on each step of my algorithm is something similar. I want that it has a meaning of divergence, so that's why this HQ diff, and the divergence is close to the source term. Okay, so that's basically the physics behind. On each step of the algorithm, I want to have some vector fields which are, if possible, in equilibrium with the data. And typically, I don't achieve this with equal sign, so that's why the second object here appears. And this is kind of something which will always come from linear algebra. If my linear algebra is solved to 0, this row is 0 as well. If I do have linear algebra, I'm typically, it's impossible to achieve the equality, so I'll have some object here. All I need for theory that it sits in a good space, well, it will be some piecewise constant typically for finite volumes. And you can somehow feel that I would like this object to be small, so that not to disturb too much my equilibrium here. Okay, so this is my first assumption, A. Well, my assumption B now goes towards what I somehow intuitively feel. So if my processes contains discretization, then linearization, and then linear algebra, they will be these 3 sources of the error. And I somehow want to encode these sources inside of this vector field TH. So the assumption is quite simple. I just wanted this TH that I call total flux is decomposed into 3 parts. And in a way that these 2 parts, this L and this A, are once again something small, or more precisely that this L will go in appropriate norm, and this is my setting now, it will be LQ norm, that it goes to 0 whenever the linear solver converges, and then this A, which will represent the algebraic error, goes to 0 as the linear solver converges. Okay? Well, and what is the meaning of this T? Well, it's precisely somehow encoded in my last, third assumption. I want this D to be something, of course, which is close to the flux of your scheme, the flux of your scheme. So you take your nonlinear flux function, you plug as the argument the current approximation, and this gives you the flux. And this D, of course, should be as close as possible to this flux. So these are the 3 assumptions. And well, this is rather vague. Of course, we have a precise way how to state it, but for this presentation, I've just chosen to say it should be small. Okay? So, and with these 3 assumptions, I'm ready already to prove mathematically a lot of results, which are resumed on this slide. So, the first result works under these assumptions A and B, and shows that the distance between the U, which is the weak solution that I do not know, this UHKI, the current approximation by your favorite numerical method, the distance measured in the sense of this quantity that I will describe a little later. Definitely it's an unknown quantity, it's the error, can be upper bounded by your a posteriori estimator, this is here on the right, and the estimator will have the different parts of the error, discretization, linearization, linear algebra, and also something related to this row here, which we would like to have small. So this is under A and B, and now under assumption C, and there is a much more work to prove this simple looking line, but under assumption C, what you can also do, you can prove that this computable number, this a posteriori estimator, is on its turn a lower bound for the unknown error, this time with some generic constant, but what you know that this generic constant only depends on the regularity of your mesh. So it in particular does not depend on how nasty your problem is, so it does not depend on the size of the nonlinearity, it does not depend on this Lebesgue exponent, so it gives you an equivalence between unknown error and new estimator in proper robust setting. Okay, so what are now these numbers? Because if you want to code it, you would like to see what are these estimators. So the estimators, they are here, and they are rather simple. I maybe start here with this linearization and this algebraic. Well, you've already seen that we would like somehow to decompose our total flux and have these two objects which should be small as the solver converge. So not a big surprise that they come as our estimates for algebraic error. So the LQ norm of A is the estimate of the algebraic error, and LQ norm of L is the estimate of the linearization error. This is also not a big surprise. It's like the error in your constitutive relation. The discrete flux, you compare it with your reconstructed flux, and that's the discretization error scheme. If your approximation is non-conforming, then there will be something linked to the fact that you're missing the conformity. So that's the second part of the discretization error. And these are the three main ones. And I've mentioned that we are not too happy about this row, which appears, once again, only when linear algebra is not converged fully. But, okay, it is there. It will appear in the upper bound, and it will appear in the LQ norm, preceded by a constant from the Friedrichs inequality, and this one is rather pessimistic, is the diameter of the whole of omega. And so we see this will kind of force us to make this term small enough so that this is not dominating. So this is it. I mean, if you want in this very simple setting to have an overall picture and to be ready to code it, you basically need just from your particular scheme construct these three vector reconstructions, and you measure them, and this give you a posteriori estimate. Okay, I will just show you how does. I think there's one slide. Okay, saying that now these three assumptions, they have been verified. We've amused us, that's a paper with Alexander, to verify them scheme by scheme. So for all these different schemes, and for different typical linearization like fixed point and Newton, and basically for any linear solver. So we have amused us to verify this A to C. So you've got this equivalence of the error and estimate for all these settings verified. But I don't want to spend much more time on this. I want to show you some results, how does it work, and then pass this two-phase and three-phase to show you how these quantities, L, A, and D, can be obtained in two-phase and multi-phase setting. So before coming to this, some pictures. I hope they will be fine for you. So first set of results will be presented for my P Laplacian for two particular choices of P, one on the left of 2, one on the right of 2. It's a test case where I know the solution. It looks for P equal 1.5 like this, P equal 10 like this. And for one chosen discretization, it's the piecewise affine non-conforming, so-called Crouzet-Raviard finite element method. It's the choice of the discretization, and then, as it's somehow noted here, the linearization was the typical Newton method, and the inner algebraic solver, these were conjugate gradients. We are now on some chosen mesh, which is a sixth refinement of one starting mesh. we've got our system of nonlinear algebraic equations. We started to do Newton. We stop on its 6th step. And then we will look on what's going on in terms of the CG iteration. So here, what is on my x-axis is the number of conjugate gradient iterations. What I'm plotting is the overall error, or more precisely, in red, the error, because it's a test case, I know the error, and all the other curves are our estimators. Okay? First, what I observe for the error. Or in this setting, fixed mesh, fixed linearization step, the overall error in terms of algebraic solve iteration would go down a little and then stagnate. Well, why so? Well, the understanding is given by our estimators. It's typically because the other components of the error, linearization and discretization, they will not go down when your algebra converges, so they will block the total error to go down. It's rather natural. The point, however, which all this allows you to do is what I mentioned on my motivation slide. It allows me to see, okay, I don't need to push this green curve, the algebraic error, too much beyond the point where it becomes negligible in front of these other components, and I just stop there. So I stop after something like 30 iterations, whereas, and it's now picture on the left, is taking the thing to this extreme, doing the full Newton method. If I would like to solve my linear system, I would need 650 iterations before my algebraic error, it's not of course 0, it's only 10 to the minus 8. So this is like a practical message of what we are doing. One practical thing of this distinction of these different error components is that you can compare them and you can stop at a good moment and you don't push your solver too far. Well, of course, people had ideas like this before, and that's the inexact Newton itself. This is this middle picture, and it's something which works rather nicely, except of the fact that you don't have the real knowledge of the things. So you're not sure if you should stop after 15, 20, or you will not go to 650, but you don't really know how much is the good. And that's the adaptive inexact Newton with all these curves tells you that's the good point to stop. So this was how all these estimators evolve in terms of algebraic solve iterations. And basically the same picture now, once we say, okay, we are happy with the algebra, and we now continue the iteration of the linearization solver. So we observe the total error, the red curve, the estimate, the blue one, so both of them are somehow here, and then the two resting components, the discretization in black and linearization in terms of Newton iterations. Once again, typically you would iterate until your linearization error is rather small. This is the full Newton, and you would need something like 20. And if you do our adaptive version at around this point, you see that it's no really good idea to push the solver further. So in overall numbers, you obtain something like this. So still here is error. Now on this slide, there's no more error. Here I have first the number of Newton iterations, and I take a sequence of meshes, and I observe how many Newton iterations I need for mesh level. So full Newton method, it's known to have at about a constant number, which is beautiful. In our setting, you have something like this, but even with some economy. And that's the inexact version, which needs quite some increased number of Newton iterations. This is number of algebraic iterations per Newton step. Well, this inexact Newton, we fix it, so that's why it's constant, 15. The full Newton, we've seen it can go up to 650. And this adaptivity is very well seen here when 2 or something like 5 iterations of linear algebra per Newton step are okay. You do 5. And if you are in a situation where the context is such that it needs more linear solver iterations, you go to a bigger number. If it's finished, then you will decrease once again. That's the adaptivity. And there's this overall gain is on the right. So this is the overall number of algebraic solver iterations per refinement level. With full Newton, you get something. With engineering approach, you cut this number by a factor roughly 5. And if you do this adaptive version, you divide once again by something like 5. So this was to show some results, and this I will go faster through. That's the same results, but I've changed my p-index. I go to 1.5 instead of 10. The overall picture is more or less the same. To wait until you've solved your linear system will cost you a lot of iterations, and then it's not really meaningful. You need to go over a large plateau, and then only your algebra starts to work nicely. But it turns out that you could have stopped here, and that's exactly what happens in our picture. Okay, and this inexact Newton here is not at all enough. You need more than 15. You need almost 100 here. Once again, the graphs in terms of the linearization process. So how does the Newton converge? This is also quite interesting. So you've got a long plateau before you get your famous quadratic convergence of Newton. And kind of my feeling beyond, or my explication is that, well, the error is elsewhere than in the linearization. So it's not really any point in pushing your Newton beyond this. The error comes from discretization, so the problem is elsewhere. So you should do something else than push the pure Newton method to converge. So that's just what happens here, is stop after 3 iterations and change the mesh. Okay, one last example before I go to two-phase. It's still P-Laplacian, but now I've taken the L-shaped domain and I've got a singular solution. So I'm adding another level of difficulty, this time linked to the solution itself, which is such that here in this re-entrant corner there is a singularity. And I'm just showing a picture where we've now somehow matched, put everything together. So we've got the stopping of linear and nonlinear solver. We know all the components of the error. We know the discretization error. And we've seen before that it's big here around the corner, so we started to refine the mesh. And this is now the picture after I've basically resolved the singularity here. And it appears, that's the exact error, that now these largest elements are those where the error is located. And you see the estimators, they pick it exactly. They will not force you anymore to refine here. And you should refine now your mesh in these largest elements. So it's like a combination of adaptivity in 3 senses: linear solver, nonlinear solver, and mesh refinement. And there are some graphs which are possible for model problem, and I think are quite nice. So I'll spend some words on it. So this first curve is how does the energy error now goes down as in function of number of degrees of freedom, which is a number of mesh faces. And this first curve is when you do uniform mesh refinement. Well, uniform mesh refinement will never go faster than the regularity of your solution, and the regularity of the solution is not good, so you're going down with a slow speed. And that's the usual benefit of adaptivity. The point here is that of mesh adaptivity, but where you spared a lot of effort on solving these systems. In adaptive mesh refinement, this speed of convergence gets much faster and gets optimal in terms of the number of degrees of freedom. So this is this left picture, and the right one, this is my favorite, it's like a commercial. So this left one tells me that with adaptive mesh refinement and all these adaptive stopping criteria for solvers beyond, I can achieve such a precision, 10⁻², for this little more than 10,000 of elements. So 10,000 of elements, adaptivity, I achieve this precision, and uniform, I achieve this precision. And now this right picture, for each of the points that you see here, it also gives the price I needed to pay to get there. So I would first expect that to get to this point here or here would be at about similar price, because the number of degrees of freedom is the same. But the right picture shows you that it's not the case. With this uniform mesh refinement, the prices to get those to those points, they rise a lot. So in total you needed something like 550 linear solver iterations to get to this point, and you only had this precision. And now with adaptive mesh refinement, for the same number of degrees of freedom, you get to much better precision, but in fact the price to get to here was still 3 times less than the one that you needed to get here. So it's, I would say it's like a commercial, you know. You pay less and you get more. It's beautiful, right? Okay, we are happy to see these pictures ourselves. Okay, so I now move to the real heart of my presentation. First two-phase and then multi-phase, multi-component. I still have some time, right? Okay, so the two-phase flow, all of you know the equations. I take immiscible, incompressible, non-wetting and wetting phase. I look for 2 saturations S alpha and 2 pressures P alpha. I've written this usual formulation where I've expressed explicitly the Darcy phase velocities for each of the phases. Of course, plugging this expression here, you are left with your S alpha and P alpha unknowns. So these are the algebraic, the partial differential equations, and these are my algebraic constraints, and you all know of this. It's coupled, unsteady, nonlinear, etc., etc. So in this two-phase flow, I will now go a little mathematical. So sorry for those who don't like this, but I want to do some rigorous mathematics. And the only way we've been able to achieve this, it was with Clement, is to go the way of global pressure and Kirchhoff transform, etc. So it's here. I take my original unknowns, which was at the occasion this wetting pressure. I add some integral transform of my lambda, and I create a new variable, which is this calligraphic P, the global pressure, and by a similar integral transformation, I got my complementary pressure. Well, even for myself, I always include this comment, so it's not really necessary to be scared of these things. In particular, the 2 objects that you like from the physics beyond, the Darcy velocities, the U, W, and UN, they can be expressed, and this is now like a new Darcy law, which works for these 2 objects, for P and Q. So you see, once you have P and Q, you have these 2 Darcy velocities. Well, why do we introduce these 2 objects? This is because it appears that with these 2 objects, you have now access to a correct mathematical formulation of a weak solution. And in particular, it appears that these 2 objects, the global and the complementary pressure, are such that mathematically they are sitting in the correct space, which is L20T, H10, or H1 part of your Dirichlet domain. So this is the reason why we did this transformation. And well, with this writing of Darcy velocities, the weak formulation I think is not at all scaring. It just follows the physics. You've got your time evolution term, your source term, and then these Darcy velocities just expressed out of this P and Q, and this is it. Okay. So we needed this weak formulation so as to be able to do rigorous form of the upholstery estimates, where the first point was to start from this weak formulation, so these 2 lines here, and define a number which will characterize the error in the numerical resolution. So now I've got some H tau indices, so I did some space-time discretization, and I got an approximation of the wetting saturation on a wetting pressure, and I define a number in function of these 2 objects, which is some quantity which stems directly of my weak formulation. Okay, this is nothing but taking the difference of this true and approximate saturation and true and approximate Darcy velocities as expressed from these continuous and approximate functions, and look at them in the weak form, or another thing is you can call it the dual norm of the residual, because of course these terms with exact solutions by your weak formulation will give you the source term. Okay. So this is now well-posed quantity which measures the error in your numerical approximation, and I promised, we've seen this calligraphic J before. It is the same J I've used before in my steady case. Okay, so that's the dual norm of the residual, And you can somehow feel from my previous slides that this number is the one I can easily control with my a posteriori analysis. Well, we of course did this, but before, and this was thanks to Clement a lot, there is an answer for me on an important question. So does this number, this way of characterizing the error, the dual norm of the residual, is it and how linked to some more interesting or more standard measure of the distance between approximate and true solution? And this is this theorem here. So if the couple SW-PW is the true saturation and pressure of the wetting phase, and if these same quantities with indices h tau are some approximations which are now such that these integral transforms, they sit in the correct space and for simplicity satisfy initial and boundary conditions, then we can prove that this number here, the dual norm of the residual, is something which, up to a constant, upper bounds the much more usual way of looking on the distance between numerics, approximation, and true solution. So it's L20 TH-1 for saturations, L2, L2 for this complementary pressure, and L2 H10 for these global pressures. Okay, so I insist on this slide because from now on I will only be interested in this quantity, and I will show you how do I bound this quantity. Now, this slide is to tell you that whenever I bound this, I'm bounding the error in this precise mathematical sense. Okay, so how do I bound my dual norm of the residual? Well, this now gets me back to my first part of presentation, this adaptive Newton, the setting, and the results we have are basically extension, similar in concept. So now for each time step n, for each linearization step k, and algebraic solver step I, the current approximation, so which now have these triple indices nk and I, this way of measuring the error, the dual norm of the residual, can be fully upper bounded, now with constant 1, with something which is fully computable. These are the estimators, and the estimators of course distinguish the different parts of your error. So here discretization from space, from time, from the linearization, and from linear algebra. Okay. So I now have probably the heart of the presentation, so hopefully I have not lost you. The goal is now to show you what are these numbers for this two-phase setting. Okay. So for this, I specify now what is my numerics. I take the vertex-centered finite volumes. I specify the formulation. The formulation will be such that I first do the sum of my equations so that I obtain something which is always positive. And I take the approximation of this term from the previous linearization step, so it's k-1 here. And I will be looking for the approximation of the wetting phase pressure on the step k, leading me to a system of linear algebraic equations for this, the unknown. Okay? And whenever I've computed this pressure of wetting phase on step k, I'll go back to one of my saturation equations, and I recover in an explicit way the saturation on step k from this pressure on step k. So it's like the impasse, but in fact I will iterate over this k in a way that I've resolved it sufficiently. And of course, this will be my linearization procedure. So this is like one step of the linearization. And of course, I want to add linear algebra. And linear algebra will be only added here, because this is explicit. This is a system of linear equations. So I'm adding the algebra. And it means that I will have second index I. I will get some approximation with triple indices nki. And my system here will not be satisfied to 0, will be satisfied up to residual coming from linear algebra. And then once I have this P and nki, I recover explicitly my saturation. So that's something which is already in your code whenever you have a vertex-centered finite volumes with this iterative coupling. And now how to add all those a posteriori estimates? Well, it's via these fluxes. Basically, I only need to recover 3 of them, D, L, and A, as I've exposed to you. Oh, it's a little more complicated. I need now each of these fluxes for each of the phases. The way I do it, I first recover the sum. So this T, this stands for the sum of D for the two phases, of L for the two phases, of A for the two phases. And I mean, this is just the way how I do it. I prescribe the normal component of these objects that I will look for in Ravier-Thomas basis, and I define them by the normal fluxes of these objects that I have from my scheme, and this is because I do vertex-centered finite volumes, and I know that they will have local conservation on the boundary of the dual volume. So I just take what is already in the scheme, and I lift it to prescribe this D. See, so this D is defined from the approximation of the flux with your scheme. Now, this is the way I define the D plus L. Well, you can see that the difference of these two lines is the definition of L. What is the difference of these two lines is basically a difference of the terms which were here expressed on the previous iteration step and here on the current. So you see that's the linearization error. Basically, you lift the linearization error to HDiff. This is what gives you the L. So that's how I obtain the L, and this is also why the L will go to 0 whenever your linearization will converge, because then these objects will get the same. And finally, the A is all algebraic trick. You are on the step I of linear algebra, and you do some new step in advance, and then you compare what you had as the prevision with what you have currently, and this is the A. And basically what is missing is this row. And you take this new as big as necessary to make the row term small enough. Okay, and this is it. So that's our total velocities, and like this you get the same quantities only for the wetting phase, and then, as I've said, those for the non-wetting phase are just a difference, and that's it. So, and this is all you need to now. I did not put the formulas, but this is what is beyond these quantities, as I've shown in the nonlinear Laplacian. So you only need to have all these vector fields to define your estimators. So you have vector fields, you have the estimators, and you can check how does it work. This is a model problem which we've taken from some literature. It's two-phase. I've suppressed the gravity term, but I've kept relative permeabilities, and I've kept the capillary pressure. So it's, I think, a correct two-phase setting. These are data that we've used. So it's like the usual two spot. And I will be showing the pictures, which are more or less the same as for the steady case. I've got my algebraic error component here. When I iterate linear algebra, it's only the algebraic error component which goes down. And I'm not pushing it to the usual stopping criterion, which would be quite small, 10 to the minus 8 here. I only stop whenever the algebra is not too big in comparison with the other linearization, time discretization, and space discretization. And the same for now the linearization, which is done via this iterative coupling, so I only stop here instead of here. These are some overall numbers. So if you did with your linear algebra done in a way that the relative residual is 10 to the minus 13, you get this. In our setting, you only end up with relative algebraic residual 10 to the minus 6, which makes you to bring the number of no, this is linear algebra, this is linearization. This number of iterative coupling goes from something like 10 to roughly 3 per step. This is back to linear algebra. That's the number of GMRS iterations that you do per time and per iterative coupling step, in blue classically and in red with this adaptivity. And that's the overall picture. When you sum all the algebraic iterations, you get something like this. And when you do this adaptive stopping criteria, you go something like 15 times faster. So that was my two-phase. There's one picture, and I think this is it. So this picture shows you once again how you can put all together. So this was one fixed mesh, and I observed something. And then, of course, I stop my linear algebra here. I stop my linearization here, and then I start to do the last adaptivity in this setting, and this is space mesh refinement. And you see the mesh is, as you would expect, refined along the boundary between the saturated and unsaturated region, and it follows the front, and it will de-refine the mesh elements when it's not anymore needed. So this was the two-phase, and now the same story for the most complicated. We have tried to look on so far multi-phase, multi-component. So here I will have no more space to give you all the details. So we'll still have some set of partial differential equations. Well, they will now be expressed component by component, and there will still be some fluxes. These are these letters here, and of course there will be some coupling condition which will add you the algebraic constraints. So there is a little about the constitutive laws. So you've got phase by phase pressure, which is obtained from reference pressure and the capillary pressure. There is still a Darcy law for phase velocity, but what appears here in this component flux is a combination of all those Darcy velocities, which are here, over all the phases present in one component. So it gets much more complicated, but still there is, for us, an important thing, this structure. So it's some evolutive PDE, and you've got a divergence operator applied to some flux. And these are the Crozier equations. They are much more complicated. So the sum of the saturations of phases is 1, and similarly for the concentrations inside one phases. So this is all the time true. What changes is that mathematically we don't have this nice formulation. We don't have this setting where we know that there exists one and one weak solution. To my knowledge, or if you have some indication, please tell me, but I haven't seen. Okay, so what we do here, we do hypothesis. So we suppose that we are in such a nice case that we are happening to have pressure phase by phase, which is, as we had this global and complementary pressure in two phase, so which is L20 TH1, and we're supposed on top of it that these concentrations of moles are such that when you need to operate with them in terms of partial derivative with respect to time, you happen to be able to do so. So we suppose that they are in H1 0 TL2. So these are now our assumption that they exist. Well, and whenever exists, basically we can repeat the same thing we had before. And I would just like, in those couple of last slides, show you how we can now obtain all the quantities that we need for our upper stress estimates, and this time with cell-centered finite volumes. Okay? So I don't show the slides on how do we estimate the error, it's always the same. The point is we'll need to define these three fluxes, A, L, and D. To define them, I first need to show you what is the scheme. So this is the scheme. This is what you already have in your code if you have full implicit cell-centered finite volumes for multi-phase, multi-component. So on each time step, you have by discretization, by cell-centered finite volumes, a system of nonlinear algebraic equations. You define the Newton linearization, and you set your favorite solver to solve this system, and consequently you will obtain mesh element by mesh element one approximation of the global pressure of the reference pressure and of the saturations and of the concentrations, which will satisfy this discrete version of your PDEs, where in particular, because you do cell-centered finite volume formulation, you go here mesh phase by mesh phase, and you get quantities which naturally represent fluxes. The fluxes are here, and because I've said I do Newton linearization, the fluxes are such that they can be written explicitly, and this is this line here and this line here, by the Newton construction. So the given flux is the one that you had on the previous linearization step, plus the derivative of your flux function in the previous linearization step and the difference. This is crucial what we'll use in our construction to obtain our flux A, which will represent L, which will represent the linearization error. So this is the structure of the object that I already have in my scheme, and no, skip this. Oh, I did not put it. Whoa, that's a pity. Okay, well, so I'll just say orally. So the structure that is in the flux of the finite volume itself is something I will use in my A construction. So the A, the vector object, which be such that its normal component on each face is given by, so the L will be flux which will be given by this object, the flux that you obtain by Newton linearization, minus the one that you had on the previous time, and that's it. So that's how I obtain the L, and similarly for the other ones. I thought I put it, okay. And then, well, that's the usual result I've shown you before. On time step n, linearization step k, and iterative algebraic solver step I. The total error in terms of the dual number of the residual can be bounded by these quantities which represent the different error components. So what I do have here are some numerical results. So it's a two-spot setting. There are two phases, three components. We did both homogeneous and heterogeneous permeability distribution. And this I've already somehow advanced. It's full implicit self-centered finite volumes, Newton linearization, and it's GMRS with ILU0 preconditioning as the algebraic solver. So you've seen these two pictures yesterday already. So now in full resolution. And they are all the way the same. I look on what's going on with my error components first in terms of algebraic solver iterations. I noticed that usually I would go up to here. Now you see the numbers are much smaller because I heavily use quite expensive preconditioning. So typically I will go to 30, and with adaptivity I stop after 3. That's for a linear solver, and this is for the nonlinear solver. I don't need to go, in this case, to 6. I can stop after 3. And once again, similar pictures as before. How I can, in the overall view, break down the number of Newton iterations from, say, 5 to 1 or 2. And the very much final picture, what about the total cost, which for me is the cumulated number of Newton, that's the first Newton iterations, and there will be algebraic here. So first the Newton iterations. When I run over my simulations, the total one will be something like this with usual. I can halve it roughly with stopping criteria for linearization solver. And when I add on top this stopping criteria for algebraic, we've seen it goes down from 30 to something like 3. I can break down the total final overall cost when I sum over all time levels and all Newton solvers from something like 54,000 to 5,000, which is in this case a little more than a factor of 10. Okay, so I think you're all waiting for your train to depart. So I've said I will try to stop earlier. So we are there at the end. Well, I think the message is clear. If you've got a nice way how to recognize if you can stop early or not, it's better to do only the necessary number of algebraic or linearization iterations. And all of this is possible because you see how your error is composed. So you can do what I think is more and more popular in today's world. You decide online, right? So you decide if you do linear algebra or linearization or space mesh refinement or time modification. And we've seen that you can really gain some time. And on top of it, don't forget you always know how big is the overall error. So you know if you've computed something reasonable or not. So we are working on other coupled nonlinear systems right now. And we started to look at these two issues, which are, I would say, rather non-traditional for a numerical analyst. And is that to show that these approximations that you get with indices nki, so something which is not covered by the usual theory, because the usual theory requests you, the solver, to be converged to the very end. And you want to show that these nki indexes objects converge to the true solution. So for instance, the mesh does not need to be refined everywhere. You just refine there where needed, and still you converge to the true solution. The solver does not need to run to the very end. You just need to make sure that it's resolved sufficiently. And you still converge, so this is this word, and optimality, that is then that this happens with the cost, which is typically proportional to the number of your unknowns. So it's linear cost. You never go more than linear. So you don't spend any more, something like quadratic number of iterations to solve your linear system or something like this. And this is just a list of 4 papers where basically you find all the details of what I've presented. So, thanks a lot.